Hello! Welcome to today's lesson on voltage and how it relates to energy transfer in electrical circuits. In this lesson, we will firstly explore the concept of voltage and discuss what happens to electrons when they pass through a cell. We will then understand the work done in the cell and examine energy transfer to electrons. Finally, we will understand the formula for voltage and the associated units of measurement. So far, we have discussed how electrons flow in a circuit. We established that cells don't directly supply electrons, but create a push voltage that causes their movement. You should also be familiar with current. In our previous discussion, we learned that cells don't directly supply electrons, but create a push that causes their movement in a circuit. This push is what we call voltage. Let's explore it further. Electrons flow from the negative terminal to the positive terminal in a circuit, as they're attracted to the positive terminal. However, what about when they have to pass through the cell itself? When electrons pass through the cell itself, they have to go from the positive terminal to the negative terminal. The negative terminals repel the electrons. Hence, to make them pass through the cell, work needs to be done to overcome this repulsion. For every charge passing through the battery has to transfer some energy to it for it to be able to successfully overcome the repulsion and pass through the battery. This work done on each electron passing through the cell is referred to as voltage. Voltage is the push causing electrons to move through a circuit, facilitating the flow of electricity. As electrons pass through the cell, energy is transferred from the cell to the electrons. Then, as electrons flow through the circuit, they transfer this energy to the components, which convert it into various forms such as light and thermal energy. Hence, this push provided by voltage is crucial for transferring energy from the cell to the components within the circuit. Voltage is quantified as the work done per unit charge. For example, if a cell transfers 10 joules of energy for each coulomb of charge passing through it, then it supplies a voltage of 10 volts. If a cell transfers a total of 30 joules to 3 coulombs of charge, this means it transfers 10 joules to each coulomb worth of charge, so it also supplies a voltage of 10 volts. Voltage is calculated by the formula voltage equals work done divided by charge. In symbols, this is V equals W over Q. Work done is the energy transferred to move electrons through the component and is measured in joules. Charge refers to the amount of charge passing through the component and is measured in coulombs. Voltage is measured in volts. You might also hear voltage being referred to as a potential difference. Before electrons have passed through a component, they carry a lot of energy, but after they pass through it and transfer some of this energy to it, they have less energy. Hence, there's a difference in energy levels of electrons before and after passing through a component. This leads to what we call a potential difference. In your answers, you can use either the term potential difference or voltage. This understanding of voltage is foundational in explaining how electrical energy is harnessed and utilized in everyday applications. In today's lesson, we explored the concept of voltage and its crucial role in energy transfer within electrical circuits. We learned that voltage, or potential difference, is the push that causes electrons to move through a circuit. This push is essential because it enables the transfer of energy from the cell to the electrons, allowing them to overcome repulsion and flow through the circuit. By grasping these concepts, we can better analyze and design electrical circuits for a wide range of practical uses.